All right, I want to talk briefly about a topic that does not come up in our calculus book, has never been part of the AP exam traditionally, and about 5 years ago they started to slip maybe one multiple choice question about this on there. You know, in an AP exam that's 108 points, if you make 107 out of 108 with a 68 or a 69 maybe being a 5, you're going to be fine. But anyway, I don't think I've ever seen it come up on the BC exam. However, regardless, it is a topic that I usually talk about after the AP exam because a lot of college textbooks use this approach as the primary method for finding integrals. Forrester wants us to have kind of an intuitive understanding of an integral as the reverse of a derivative. So we learn to kind of think backwards through the derivative process to find integrals. And as a result, I think most of you will be able to find integrals much faster than most of your classmates in college courses, okay? However, they're allowed to ask a question about this. I think you'll see this in a couple of the progress check multiple choice questions. It's called U-Substitution. Okay, it's a much more formal way of finding integrals. Again, I don't prefer to use it. When I took Calc 2 at UK, I didn't use it. Everybody thought I was some kind of sorcerer because I could find integrals in like, 10 seconds. So it is a little bit slower, and for a lot of people, I think it can be a lot more complicated. But maybe in some really tough cases, it can be good. And conceptually, from a theoretical background standpoint, it is technically what we are doing when we think backwards through an integral. So it's good theory to think about anyway. All right, so the idea here is U-substitution is how some books teach integrals when you have an inside function, okay? Specifically how you handle the chain rule. When we do the chain rule, we look at this and we kind of say, okay, the derivative of the inside function is 2. What do I need as the derivative of my inside function? I need a 2, okay? So we multiply our function by 2, we balance it by dividing by 2 on the outside of the integral, and then we work backwards, okay? U-substitution does the same thing, it just does it with a little bit more work, okay? So here's the idea. Typically, you let U represent your inside function, and I have used that notation. When we started talking about the chain rule, I did use U to represent an inside function. So we've kind of seen this, we just haven't seen the backwards version. So let U represent your inside function, okay? And the idea here would be that I want to be able to replace the inside function to get down to basically an integral that doesn't have an inside function, okay? So let's say we're doing an integral from 1 to 2 here. All right, so you would substitute in the U in place of the inside function. Now, I can't just take the integral here because this is a U variable and my integral is still with respect to x, okay? So what you have to do is you need to get this to be with respect to U. You basically need a du statement. And here's where it's going to come from. Remember from earlier in the year we had this idea that dy is equal to the derivative times dx, okay? An estimated change in y is just equal to a slope times the estimated change in x, okay? I can do that same kind of thing here. Du would be equal to the derivative 2 times dx, okay? And so I need that because I want to have a du here instead of a dx, all right? So what I need to do here is I want to replace the dx. That means I need to solve for dx. So I'm going to divide both sides by 2 here. That tells me that 1/2 du is the same thing as dx. So if I want to take out the dx here, I can take out the dx and I can put a 1/2 du in place of it, okay? Now, by the way, if you notice, this gives us exactly the same thing that we do when we think about this. We say, hey, I need a derivative of an inside function of 2. I'm going to balance it by factoring out a 1/2. Well, there's our 1/2, okay? And it's going to get factored out in front, okay? So actually, if you just look for that kind of counterbalance value out in front of the integral in a multiple choice question, that's all you need to do. Now, there's one other problem. 1 and 2 were x bounds, okay? I don't want to put x values into my function. I want to put u values into my function. So I need to convert. I can come back to this original statement. U is equal to twice the x value. So if I have an x value of 1, 2 times 1 would give me a u value of 2, okay? If I have an x value of 2, 2 times 2 is 4, and that would be my u value there. And then now you've got this real simple equation that you can take the integral of, and we can just go from there. So the antiderivative of cosine is sine. Of course, you've got the 1/2 out in front. you're going to evaluate this between u values of 4 and 2. And so according to the fundamental theorem, after we've taken our antiderivative here, we've got 1/2 sine of 4 minus 1/2 sine of 2, and that would be our final answer. All right, so again, can they make this a lot more complicated? Absolutely. But that's the basic concept, and if they ask about a U-substitution, they're really just talking about the approach that you might use to take an antiderivative. So again, I don't think you're going to see that coming up on the free response part of the AP exam, but will come up in a couple of the practice multiple choices and the progress checks. And again, if you just look out front for the balancing value, and if you convert your two values over for your bounds of your interval, typically you're going to be able to figure out the multiple choice, even if you don't really know how the process works. But it's very possible, if you go on to take future calculus courses, that your professors will use this approach. Certainly if they want you to use it, they'll probably teach it again. But again, if you're wondering what they're doing and what they're talking about, that's what a U-substitution is.